Hello friends, welcome to GT Science tutorial. In this video, I am going to explain about the jumping frequency in a crystal. This is a very important concept in solid state chemistry. This is a part of diffusion concept. If you haven't watched my previous videos, then please go and watch those videos to understand about diffusion. So in this video, we will understand what jumping frequency is and we will see the mathematical form related to it. So let's start. First of all, we need to understand what jumping frequency is. So its definition is jumping frequency refers to the rate at which atoms or ions within the crystal lattice vibrate or jump from one equilibrium position to another equilibrium position. So it is just the rate. So frequency refers to rate. Jumping means if something is over here and it needs to reach over here, and if there is no medium to connect them, then obviously it will have to jump from here to here. So jumping frequency means from this equilibrium position to this equilibrium position, this ion or atom will have to jump from here to here. Okay, from here to here it has to jump. So at what rate does it have, is it jumping? That is what jumping frequency is. So you can simply say in 1 second, the number of times an ion or atom jumps from one position to another position to maintain its equilibrium position is called jumping frequency. I hope you understood what it means. Also, the phenomenon, that this phenomenon is intimately linked to the thermal energy of the system. So it is linked with thermal energy of the system. We will see it later in this video, and it plays a crucial role in various physical processing such as diffusion, electrical conductivity, and phase translation. So jumping frequency concept is used in all these phenomena. Now let's move forward. Now, let's see the factors that affect the jumping frequency. They are temperature, potential energy barrier, mass of the atom or ion, and crystal structure. Now, let's see how these factors affect the jumping frequency. So, we will see the effect of these factors one by one. First of all, we will see the effect of temperature. So how does temperature affect the jumping frequency? Let's see that. So as temperature increases, the thermal energy of the atom also increases, providing them with sufficient energy to overcome the potential energy barrier that binds them to their lattice site. So suppose if these are the lattice ions or atoms, and if it needs to jump from here to here, some vacant position, then obviously it needs some energy. And where will it get it from? It will get from heat energy, right? It will get from heat. So if we increase the temperature of the system, then the ion next to or neighboring ion to this vacant site will get enough energy to overcome this potential energy barrier. So you can see there is gap, right? This is the gap. From here to here, it needs to jump. So the energy to jump is provided by the higher temperature. So this increased thermal energy leads to more frequent jumps, resulting in higher jumping frequency. So it also says that with higher temperature, that is with increasing temperature, the jumping frequency increases. It is a very simple concept, right? Now, the other factor is potential energy barrier. Other factor is potential energy barrier. So how does potential energy barrier affect the jumping frequency? Look at here. So we already know the concept of energy profile diagram. We already know the concept of energy profile diagram. So let me draw an energy profile diagram like this, and we usually see an energy profile diagram like this. This is the activation energy or the energy required for the reactant to convert into the product, and this is called intermediate condition, right? So what happens, initially it was in equilibrium condition, so the energy would lie over here. Now to reach from here to here, it needs to cross an energy barrier. That means there is gap, there is no medium. Now to overcome this medium, it needs to have certain energy. That means it needs to pass to certain energy level, it needs to cross an energy level just to reach to the other equilibrium position. So this is called potential energy barrier, or this gap can act as potential energy barrier. So you can see over here the height of the potential energy barrier, this height, okay, this height that an atom must overcome to jump to a neighboring site significantly affects the jumping frequency. So this height affects the jumping frequency. If the height increases, jumping frequency decreases, right? And vice versa. So a higher barrier requires more thermal energy, leading to the lower jumping frequency at a given temperature. So it all relates to temperature. Similarly, mass of the atom or ion also affects the jumping frequency. Suppose if there is a thin man and if there is a thick man, if they have to jump to a larger distance, who among them will jump to a longer distance? Obviously this one. This will require less energy to jump, right, than this person. I'm not trying to be a racist over here. I'm just trying to give an example. That means a heavier thing will require more energy to jump, okay, and a lighter thing will require less energy to jump. So those elements or ions with low number of atomic mass, or low number of atomic mass or lighter elements will jump easily, and those elements which have higher atomic mass, that is, which are heavier elements, will not be able to jump with little amount of energy. So you can see over here, heavier atoms or ions generally have lower jumping frequencies. Obviously heavier will have lower jumping frequencies, right, compared to light ones, as they require more energy to overcome the potential energy barrier. So I hope you understood it properly. The fourth one is crystal structure. Crystal structure will also affect the jumping frequency. You can see over here the arrangement of atoms or ions in the crystal lattice influence the potential energy barrier and the available pathways for jump. So we know that generally, like we see BCC and FCC structure of crystal. This is body center cubic structure and this is face center cubic structure. Its coordination number is 8 and its coordination number is 12. That means one ion is surrounded by 8 ions in BCC structure, and one ion is surrounded by 12, total of 12 ion in FCC structure. So if an atom has many vacant site, okay, sorry, if an atom has a vacant site over here, then neighboring atoms can easily pass through it if they have less number of atoms. That means if it does not feel much strain, I'll talk about strain later. If this atom does not feel any strain while other atom is trying to jump over here, then obviously potential energy barrier will be less. So we can say that crystal structure actually affects the jumping frequency of the substance, or jumping frequency of the atom or ion. Now let's move forward. Now we need to understand about the jumping frequency in vacancy and interstitial mechanisms of diffusion. So I have already explained about vacancy and interstitial mechanisms in diffusion in my previous videos. Here you can see a potential energy diagram over here, right? Energy profile diagram over here. In the y-axis there is energy, in the x-axis there is distance. So you can see this condition is represented like this. Here an atom is over here, which is at the equilibrium position. Now if you see properly, this is a vacant site. So an atom has a neighboring vacant site over here, or adjacent vacant site over here. But initially, as it was in equilibrium, it has low energy. That means it was stable. Now as this atom is trying to move to this direction, we can see one thing. We can see over here. See, these two atoms, this atom and this atom, felt strain because it could not easily pass through them. So as a result of that, this atom will move up, this atom will move down. That means this atom will push both of these, right, in opposite direction. That means there will be a creation of local strain over here, and as a result of that, it will have a higher energy. Its energy will be higher, it will be unstable form. And when it finally reaches to the other side, that is on the vacant side, a new vacancy will be created in its original position, and this will also be a stable form. That means with a low energy. So I hope you understood this energy profile diagram. I've just written the same thing over here. That means, look at here. In solid, rearrangement of atoms occur spontaneously to form a more stable state. We know that rearrangement of atom occurs only to have a more stable form. However, atoms must have enough energy to overcome an activation energy barrier to change from an unstable state to a stable state. So you can see over here, if this atom did not have enough energy to overcome this energy barrier, would it be still possible to form a new form? No, it would not be possible, right? So this energy would be provided by thermal energy, and this will provide this enough energy to this atom to move from this position to this position, and it finally moved over here. And when the diffusing atom, that is, this is the diffusing atom, squeezes between the other regularly lattice atoms. So this is the diffusing atom. These are the other regularly lattice atoms. The latter are displaced. Latter means these are displaced. You can see over here, these are actually displaced, right, from their equilibrium position. This induces a local strain in the lattice. This has induced a local strain in the lattice. Then the strained lattice is at a higher energy configuration. That means it is over here. This is represented over here. And this EM is the activation energy. Now, to understand about the mathematical form of jumping frequency, we need to consider few terminologies. That means, like EM. EM is the, I've written a very long language over here. Simply you can understand EM is the energy required, it is energy needed for the occurrence of diffusion motion. That means what is this? This is the activation energy. Activation energy. Activation energy. Similarly, EV is the average energy needed for the creation of vacancy. KB, Boltzmann constant. T is absolute temperature. Now there are few more terminologies that we need to introduce over here. That is V naught, VO or V naught, which is the abbreviation for uh, lattice vibrational frequency. Vibrational frequency. And similarly z over here is z over here is the number of equivalent neighboring site. Number of equivalent energy, the number of equivalent neighboring sites. So these are the few terminologies that are used in the mathematical form of jumping frequency. We don't actually require the whole derivation of jumping frequency. We just need to understand the formula. Okay, so the actual formula for the jumping frequency, that is denoted by F. This is jumping frequency. Okay, jumping frequency will be equal to Z V naught exponential minus EM plus EV by KBT. So this is the formula for jumping frequency. Let us consider, let's not consider any equation. This is the actual formula of jumping frequency. You can see over here, there are two separate terms. Exponential, they are exponential minus EM by KBT and exponential minus EV by KBT. These are the two forms that are used over here, right? So what is the meaning of that? So the first term over here, that is this form, is actually the fraction of time at which the atom has sufficient energy to cross the barrier. Okay, so this represents fraction of time for the atom when it has sufficient energy to cross the barrier. Similarly, this form over here represents the fraction of time at which atom has a vacancy nearby. So EM represents the jumping frequency. Sorry, EM represents the possession of sufficient energy by the atom. EV represents the uh, neighboring site having a vacancy. Without vacancy, it cannot diffuse. So this is what you need to remember. This formula is very important. Okay. Now we just talked about, look at here, we just talk about a diffusion, right? But what if we talk about interstitial mechanism? So in interstitial mechanism, look at here, suppose if these are the atoms, and if an impurity or another atom is over here, and if it wants to go to other interstitial site over here, then does it have to produce any strain over here? No, not at all. It can easily pass from here to here. It does not require a higher energy, right? So in this case, in this particular case, wait a second. Yeah, in this particular case, does it require this much of activation energy? No, not at all. So if we talk about interstitial mechanism, the energy profile diagram would look like this. This value would be em. This value would be em. You just have to draw a new figure like this, okay? So its mathematical form, similarly, its mathematical form for interstitial diffusion, for interstitial diffusion, the jumping frequency which is denoted by F will be equal to ZV naught exponential minus Em by kBt. Here in this case, we have just neglected or eliminated the form EV because we don't require any vacancy near it. Other forms will be same. This is the formula for the jumping frequency in the case of interstitial diffusion. That's all in this video. If you like the video, please share this video as much as you can, and thank you for watching the video. And please don't forget to subscribe my channel to make my face look like this. Thank you. Bye bye.